Good morning again, everyone. Welcome. This is Modern Algebra, and we're going to start in with the next series of notes. Our goal is to build up to the definition of a group, which is one of those abstract structures I mentioned in the introduction. That definition is somewhat intricate, so first we will build up to it with the ingredients that we need, starting with the idea of a binary operation. So, suppose we have a set of objects, S, any set, and we've talked about sort of intuitively operations like adding and multiplying and things, and I want to make that formal. I'll give a definition now. What exactly do I mean by a binary operation on S? So definition, we'll say that star, we'll use the symbol star. Star is a binary operation on S. That means essentially that for any two things in S, for any inputs A, B coming from S, there will exist a unique output value A star B that must also belong to the set S. For all A, B, and S, there is a unique value which we'll write A star B in the set S. So you can think of star as being some sort of version, something analogous to like addition or multiplication on real numbers. We'll see in a second that those are examples of binary operations. But notice several things. So you've got these A and B. Whatever A and B you pick from the set, there has to be a value coming out. It has to be unique. Only one value comes out for those A and B. And it has to be in the same set that you started in. Okay, S. And that actually, that might not seem important. That ends up being one of the most important things that, of all, that we have to constantly worry about throughout the course. So there's actually even another phrase that's introduced to emphasize that aspect called closure. So as a second definition, that's sort of it's already in this one, but it's also given the separate name. We'll say that S is closed under star. Closed under star to mean for any A and B coming from S, for all A and S, for all B and S, this output A star B is again in S. All right, and here I'm using some notation from proofs. You've hopefully seen this universal quantifier, the for all, the upside down A, and set membership, this membership symbol that says A comes from S, belongs to S, B is a member of S. Okay, so that's the two definitions I want to start with. And every time you have a definition, you want to memorize the definition carefully. So you've got a defined term, binary operation or closed, and you've got this other box called the definition text that tells you what that term means. Okay, and as soon as I have the definition, of course, you're going to want to have a bunch of examples and non-examples. So let's think about which of these things are binary operations. I have a whole list of them. Some will work, some won't. Let's think first about the set of integers. So you have to have the set. Someone has to tell you the set in advance. Be very clear about what the set is. Let's start with the integers. If we have, instead of star, if we just had addition plus on the integers, if you take any two integers, and there's another integer, a plus b, a unique integer a plus b, that's still an integer, okay? So that works. That is a binary operation. Similarly, multiplication on the integers, the set of integers. If you give me any two integers, multiply them, you get another unique integer coming out, still an integer, still in the set, so that's fine. And thinking back to the introduction, all these arithmetical operations, subtraction also works on the integers. That's a binary operation. And then finally division, the fourth, we'll use this symbol for division. A divided by B. Well, here finally there's a problem. There's actually two problems. First of all, you can't divide by 0. 2 divided by 0 doesn't exist. And so there's an example of objects in the set of integers where you can't do it. You can't divide by 0. So therefore, this is not a binary operation on this set because it's 0. And there's actually a second reason that's coming back to this closure idea, which is even without worrying about 0, if you had, say, something like 2 and 5, those are integers, but you try to do 2 divided by 5, which is like 0.4 or whatever, that's not an integer. It's not in the set. Okay? 2 is an integer, 5 is an integer, yet 2 divided by 5, however you want to write that, it's not in the set. You don't have closure. And for reasons we'll come to, that's not acceptable for this study that we're going to do. So we say it's not a binary operation. Okay. All right. So, and I want to emphasize the set is key. You have to know what the set is before you can even answer this question. So let's try the same operations, but with a new set. Maybe the set is going to be now the real numbers greater than 0. The set of strictly positive real numbers. And I'll ask you, meaning you should pause the video and think for a second about plus, addition, subtraction, multiplication, and division on this set. And which of these are actually binary operations? On this new set, on reals greater than 0. So think about that. All right. In this case, addition still works, but you have to think about why. If you start with 2 positive real numbers, a fact from before that you know is that the sum is still, first of all, a real number, but also still positive. So you have closure. That's true for whichever numbers you start with. So addition's fine. Similarly, multiplication is fine. The product of 2 positive real numbers is still a positive real number. And actually here, division is fine as well. A 0 is not part of this set. We're not dividing by 0. And because we're real numbers now, you can do 2/5. You can do pi over e. Any positive real numbers you want, you can divide them and get another real number, another positive real number, in fact. So it works in that set, okay? Even though it didn't work over there. Finally, though, subtraction, which did work before, does not work on this set. You cannot, it's not a binary operation on this set because it's not closed. So for instance, among many other examples, 2 is a real number, 3 is a real number, but if you do 2 minus 3, although you do get an output, positive real number, this output you get is not positive. It's not in that set. It's not closed. Okay. So we have this sort of nuance that we have to constantly check about whether it's closed. All right, now there's lots of binary operations. You shouldn't think it's always going to be addition and stuff. There's way more possibilities. And so one thing you will do a lot is just to do a finite set. So let's take, I'll just randomly pick the set 1, 2, 3, 4 as my set. Okay. And what we often do, you don't have to use arithmetic. You can just sort of make up a rule for calculating star. And it's often called a multiplication table. Although it doesn't have to be actual multiplication. It's just a term that's used. All right, and the way this works, you've all done this in like elementary school for the actual multiplication and addition of integers, but you make a little table and you put the elements of S, 1 through 4 in this case, as headers for the rows and columns. And then you just sort of fill the table in. I'm just going to sort of randomly put things in there. And this is a way of specifying a binary operation. Or maybe it's not. Maybe it isn't one. But what does it mean? So for instance, what you do, if you want to know, this table is telling you what's 2 star 3, you go to the row labeled 2 and the column labeled 3, in that order. 2 star 3, and in this case you get 4. You go to this entry in the table. So that's how you're supposed to read the table. On the other hand, 3 star 2, you go to the row 3, column 2, and you get 1. Doesn't have to be the same. Okay, we'll talk about that more in a minute. So anyway, and so you can get everything this way. So 4 star 4 is 3, etc. So we'll be having a lot of operations on finite sets, and we'll look. But then wait, is this even a binary operation on S? And actually it isn't. Why not? And you probably noticed that there's a 0 right here. So everything works. For every input A and B, you get something coming out, exactly one thing coming out based on the table. But this one case, the thing that came out was not in the set. So 4 is in the set, 2 is in the set, but 4 star 2 is 0, which is not in the set. So closure failed. Even if there's one exception, that's enough to make it fail. Of course, we could have easily fixed that by putting some number like 2 in there. And then it would be fine. All right? But anyway, see, this is another thing. You don't have to actually have a formula. Like I just randomly filled values in. It doesn't have to be given by addition or any particular formula, as long as it's just some things that are, all the outputs always come from the set that you started with. All right, just a couple more examples to emphasize that point a little bit more, that from something you've done before, the vector calculus. Maybe the set is R cubed, the set of 3-dimensional vectors with real entries. And you've all done the dot product and the cross product. Back in calculus. So here V and W were 3-dimensional vectors. And I want to ask, are these binary operations on S? Think about that for a moment. Answer, the dot product is not. It's not a binary operation. On this set, because when you do a dot product, if you remember, the thing that comes out of the dot product isn't a vector. It's a real number. So like if we did something like 1, 2, 3, dot 2, 0, 1 or something, to quickly remember dot products, you would do 1 times 2 plus 2 times 0 plus 3 times 1, which is 5. Which is fine. I mean, that's a helpful thing to do in calculus, but it's not in S. It's not a vector anymore. It's a scalar. And that's not allowed. So in this setup that we're looking at, you always have to land back in the same set that you start with. I mean, there's another name for this. It's something you look at and work with, but it's not a binary operation. On the other hand, cross product, which is a little weird, this is a binary operation on R cubed. The cross product of two vectors is another three-dimensional vector that's uniquely determined by the two that you started with. All right? So we'll continue in just a moment. All right, so let's move on to the next idea, the next ingredient. From now on, we'll have a fixed set S and a binary operation star, so closure is satisfied. And I want to introduce some properties, algebraic properties that this operation may or may not have that will be constantly useful to us. So two more definitions. Definition. I'll say that star is commutative. Commutative. What does that mean? It means that for all A and S and for all B and S, A star B is always equal to B star A. So you can change the order of the inputs, and you always get the same result. Okay. Again, using my universal quantifiers here for all. Okay. Second definition, I'll say that star, binary operation star, is associative. If you give me three things, A, B, C, all coming from S, I can form A star, B star, C, and I can actually do that in two ways. I can put in parentheses, and for associativity, it doesn't matter where you put the parentheses. Namely, and here I'll abbreviate slightly, for all A, B, C, and S, if you first do A star B, and then do the output star C, that's going to give you the same result as first forming B star C, and then doing, in this order, A star that. Okay, so the parentheses have moved. That's what associative means. Okay. Every time you have definition, you're going to want to memorize the definition, including these quantifiers, universal quantifiers, the sets that are involved, parentheses, everything like that. Another thing, reviewing proofs. Not everything's commutative. Okay, and so anytime a new definition comes along, you might want to practice by sort of negating both sides to form, what does it mean to not be commutative? Let's just do that here to remember how that works. Here's commutative. So if I wanted not commutative, which I'll abbreviate COMM, what does that mean? So you have to take this text of the definition, you have to negate it. And as you might remember from proofs, when you negate a universal quantifier, you get an existential quantifier. There exists an A in S. There exists a B in S where the identity fails. And the order does make a difference. But the quantifier is flipped. That's key. Again, remember my notation for all, the upside down A and the backwards E, where there exists. We'll use those constantly, by the way. Similarly, for not associative, which I'll abbreviate associative ASSOC. Same thing, these universally quantified, this is like for all A, for all B, for all C, becomes an existential quantifier. So if there's even a single example where the identity is not true, then it's not associative. All right, and we'll have more complicated definitions later. If you want, you could try negating the definition of closed. S is closed under star for practice. All right, and of course you want to memorize, it's enough to memorize the original definition and then be able to negate on demand, so to speak. All right, so let's look at some examples now of some of these operations we've just been looking at. Some of them are commutative, some of them aren't. Some of them are associative, some of them aren't. For a famous example that if we start on Z, the set Z, addition is commutative. A plus B is equal to B plus A for any integers. It's also associative. It's both. I won't prove it, but just to see what it looks like, instead of a star, you have a plus. And these identities are known for all integers. Also works for real numbers. So we're just doing integers here. And multiplication is commutative and associative as well. On the integers or on the real numbers for that matter. Any of these number systems I mentioned before. Okay. In this case, we have the times symbol instead. You're well aware of these facts, although you're not going to prove them. It's very difficult to prove it, actually. Sometimes just take it as an axiom about the integers that this is true. But don't think everything's going to be like this. Okay. So, for instance, if we looked at subtraction, which is a binary operation on the integers, I'm going to say that it's not commutative. Subtraction is not commutative. And here we can prove it. So it's easy to prove something's not commutative because it's existence. Just give an example. It's a proof. And almost anything you like will work. So take, for instance, you take A equals 5 and B equals 3, which are in Z. Those are integers. And you look at A minus B, you get 2. But if you look at B minus A, you get negative 2. So you didn't get the same answer. Therefore, this is not commutative. And similarly, subtraction is not associative. And again, we can just give an example. Virtually anything you try will work. I'll just randomly pick 5 and 3 and 1, maybe. And we'll calculate it. And here, so it's always going to be 5, 3, 1, but the parentheses are in 2 different places. So 5 minus 3, which is 2, and I subtract 1, I get 1. But if I move the parentheses to the other position, now it's going to be 5 minus 2, which is 3, which is not the same answer. All right? So it's definitely possible to not work. Okay. So one thing before I erase this, for some reason everyone misspells commutative. Notice the spelling, commutative, not commutative. And although I'll abbreviate frequently, you do want to be aware of these, the full spellings of these terms. All right? So let's look at even more examples and about commutativity and associativity. Let's go back to this R cubed with the cross product. Often use a little cross symbol for that. Binary operation. Is it commutative? Is it associative? Think about that for a moment. Pause the video and think about it if you need to. In this case, the answer is no for both. This is a kind of a famous example of a sort of a type of multiplication that's not commutative. And for instance, to show you that, if you remember the basis vectors I, j, k, I cross j is k. But if you do the other order, j cross I is negative k. which is not the same vector as k. By the way, if you don't remember cross products, it's not a big deal, but just as an example of something in calculus where this comes up. And for associativity, I don't want to maybe get bogged down in a really messy calculation. It's not, and there's many, many examples. Almost anything you try will give you a counterexample. And it's maybe an easy one, relatively easy. Let's try I, J. You're allowed to repeat things. When you test A, B, and C, don't have to be distinct. Okay, so this is something you look at. And if you do this cross product this way, you get I cross K, which, if I remember correctly, is negative J. But if you put the parentheses in the other position, any vector cross itself is the zero vector. And when you do 0 cross J, you get the zero vector out, and it's not equal. Okay. Now, there's other properties. The cross product has lots of interesting properties, but commutativity and associativity do not work. All right. Let's move on to another structure you've seen, algebraic structure from another course on matrices. Let's think maybe S is the set of 3 by 3 real matrices, real entries. And we could look at various operations. We could think about matrix multiplication. On this set. So if you take two 3 by 3 matrices, you can multiply them by the usual rule, and you always get another 3 by 3 matrix coming out. So it is a binary operation, first of all. And without proof, I will just remind you of 2 facts about this. Very famous fact is that matrix multiplication is not commutative in general, and at least for bigger than 1 by 1. Let me not write matrices on the board, but you can easily come up with 2 matrices that don't commute when you multiply them. But it is associative. Matrix multiplication is associative. I will omit the proof of that. And what we'll see actually is that sometimes associativity is somehow more basic and sort of easier to get to work than commutativity. So you'll have these non-commutative operations, but we will have associativity most of the time for the ones that we look at. Okay, so that's a possibility. On the other hand, there's other operations. So like you could also look at addition, matrix addition on this set. And in this case, addition is nicer than multiplication because it is commutative and it's also associative. Again, I'm not proving these claims, but I'm just citing some facts from, you have to know the definition of matrix addition to actually execute the proof of that. Now we really, okay, so we should prove something to see what a proof looks like. Let's look at, let's do a proof. So let's say, here's another operation. So suppose S is the set of reals greater than or equal to 0. This will be my notation for that. Real numbers greater than or equal to 0. And we'll have a weird operation, slightly weird. Let's say that A star B is going to be the square root of A squared plus B squared for any A, B in S. That's the operation I want to use. And square root, by the way, refers to the non-negative square root. It's not plus or minus. It's just the positive square root, or maybe 0 if you do 0 star 0. Okay. So as an initial remark, before you even talk about commutativity or associativity, let's observe that this is a binary operation on this set. And there's actually just a little bit of a check there that you have to do, which is, how do I know the square root is defined? So if we fixed arbitrary a and b in this set, reals greater than or equal to 0, then this quantity, a squared plus b squared, a squared and b squared separately are greater than or equal to 0. So their sum is as well. And that's important because I want to be able to take that square root and get a real number coming out. I can do that if I take the square root of a non-negative thing. That's allowed. That's a real number. In fact, it's a real number greater than or equal to 0, and it's unique so we don't want the negative square root. Therefore, closure holds, because notice this is the set that we started with, and we have a binary operation. So sometimes you have to go through a little bit of a proof for closure, even. But what I really wanted to do, actually, was to prove the commutativity, and believe it or not, this is actually an associative operation as well. Let's see what the proof of that would look like. We've done a lot of disproofs by giving examples, but when you prove that something works, if it's a universal statement, here are my definitions, you can't just give examples. You have to do a general proof. Okay, so let's see what that looks like. Let's prove star is commutative, the star right here, by following the definition. So when you have a universal statement, you have to fix, as I just already did here, arbitrary elements in the set S. A or B for arbitrary. Not specific elements like we did for the counterexamples, but arbitrary generic A, B, generic constants. And then we just have to calculate A star B and B star A using the definition of star. All right, so that's A star B. And now we know already that addition of real numbers is already known to be commutative. And so I'll apply that inside my square root here. First of all, this is true by definition of star. A squared and B squared are real numbers, among other things. And plus is already known to be commutative. We'll assume all those arithmetical operations, we already know that. So I can switch the order inside the square root. All right, but then I get that's B star A by definition of star. So A star B is equal to B star A. All right, and associativity is a similar idea, but maybe the details are more intricate because now there's 3 guys. And incidentally, you don't know in advance maybe that this is going to be associative, but when you write out the formula, you discover that it is, as we'll see. This time we'll fix arbitrary A, B, C in the set, reals greater than or equal to 0. And we can calculate, you can calculate each side separately and then see if they're equal. Taking very careful note of where the parentheses are. And doing one step at a time. So for this, first we're going to do A star B. So root A squared plus B squared. Star that with C. By definition of star, we don't necessarily have to write that reason every time. But now, all right, so it's tricky. So once you get an expression in there, you have to look more closely. So what do I do to this to get this star that? I take the square root, and then I take the first thing, which is this weird, ugly thing, square root of A squared plus B squared, square that. Then I add the square of the second thing, which is C, so C squared, So that's a more elaborate definition of star. This definition is for all A, B, and S, I should have said. So A and B can be replaced by expressions, and then you just manipulate the expressions. If you square the square root, you get the internal expression back. So we get that. Okay. Now, on the other hand, if I move the parentheses to over here, and I'm going to do it one at a time, B star C is the square root of B squared plus C squared. And when I do the new star, A star that guy, following this, but now replacing B by this expression here, I'm going to get the square root of A squared plus the square of this expression. All right, and of course that's going to be B squared plus C squared inside everything else. And just to have a complete proof, notice the two things we got aren't identical expressions because of the parentheses. The parentheses inside the square root are in different places. But luckily, plus, ordinary addition, is known to be associative already. And therefore, these final expressions, for that reason, by associativity of plus, these are equal. And so we do, in fact, have the identity for star that we were trying to get. And that might seem really picky, but in this class we have to be very, very careful about reasons like that. We don't want to assume, like skip a step like that. You know, we used associativity of one operation to help us get associativity of another. That'll be quite important. All right, so a few last examples about these concepts that use these multiplication tables, which are very interesting. You have a finite set, so S maybe it's 1, 2, 3. And I'll just fill in a random table here. 1, 3, just anything I want. Maybe that. All right. You can see everything in the table comes from the set S, so closure works. S is closed under star. It is a binary operation on the set, in other words, because all table entries are in the set S. As you just see immediately, 1, 2, 3. Everything's always 1, 2, 3. Is this commutative? I ask you. And is it associative? Sorry, star commutative on this set. And as far as commutativity goes, the answer is no. And what do you look for in the table when you're checking commutativity? First of all, the reason it's no is there's an example. 1 star 2 is 3 from here, but 2 star 1 is 2, and 3 is not equal to 2. And essentially what you're doing is you're checking sort of the mirror images reflecting across this line to make sure they're all equal. Like these work, and these work, and these work. But if there's even one case that doesn't work, it's not commutative. Associative is harder to check just looking directly at the table. It's not like you can just instantly look at it and see. In fact, I won't answer this here. It's very likely not, but I'm not going to commit to that before doing a calculation, because now you have to check triples. And that's not really evident from the two-dimensional table what all those triples are going to do. So check examples exhaustively is the way you do it until you find one that fails. or maybe if they all work, like every possible triple, it's lots of like 27 things to check, then it would be associative. So I'll leave that one to you to figure out. But I'll do another one. Let's have 0, 0, 1, 2, 3 as the set. And so this one will be a little bit different. So I'm going to do this, but then all this stuff is 0 over here. And I ask the same questions. Is it closed? Is it commutative? Is it associative? All right, and so you can immediately see, again, just by seeing that all the outputs inside the table come from the set, that yes, it's closed. In this case, I made one that is commutative. If you check sort of these matching entries for reflecting across this line, 0 star 1 versus 1 star 0, just visually you can see it always works. The corresponding entries every time, always, are equal. And in this case, however, I will tell you with an explanation that associativity is not true. It does not work. And so among many other examples you could look at, maybe sometimes it accidentally works, but if you look at 1 star, 2 star, 3, for instance, let's try that one, doing both parentheses. 1 star 2 is 0. And then 0 star 3 is 3. So that's 1. But if I move the parentheses, I would discover that first of all, 2 star 3 is 0. So 1 star 0, but 1 star 0 is 1, which is not the same answer. Maybe just to make sure, sometimes it does work. So if we had done just a chance led us to try something like 1 star, 2 star, 1 in both orders, I think this will work. 1 star 2 is 0. 0 star 1 is 1. And in the other parenthesization, 2 star 1 is 0. And 1 star 0 is 1. So it's definitely possible that sometimes for certain choices it works and for certain choices it does not work. That's still non-associative because associative means it has to always work. And non-associative just means just has to be a single example where it doesn't work. Okay, so let's cut that segment here and we'll continue in the next segment by talking about something that's actually visible in this table, the idea of an identity element for an operation.